Hello, my dear students. Now this is part number 2 with our angle modulation lecture. Lecture number 4, Introduction to Communication Schools. Let me first start with a quick scan, as usual, to the previous content delivered in part number 1 in lecture 4. So please allow me now to share my presentation and to start with you part number 2. So I believe now you can see my presentation, and we can now start our part number 2 with the lecture dealing with angle modulation. As usual, we will start with a very quick scanning with the content delivered in part number 1, and then we can go furthermore in the content related to this part of the lecture. So let's start. Okay, perfect. If you remember, we first defined the 3 types of modulation: AM and P and FM and PM modulation, and then we investigate the relation between the sinusoidal argument or the angle inside the sinusoidal with respect to the angular frequency or the angular speed. Accordingly, we can define 3 types of angles. Either we have a constant angle, or we have an angle where the message is included in the phase of the angle, as you can see in the phase modulation, or we have the message integrated in the frequency. Herein, the message appears in the form of an integration function with respect to the message, as you can see with respect to the time. Then we reflect this to the modulated signal, S of t. So we have 3 types of modulated signal. The first, where we have a constant phase or a constant angle, and we call this an amplitude modulation. Herein, we add the message in the amplitude, which is already covered by one lecture before, actually in lecture number 3. So we will not consider it as a part of this lecture. And then we have another 2 modulated signal with the phase modulation and the frequency modulation. Then we start to investigate a very basic example where we have a sinusoidal signal as an input, AM cosine 2 pi FMT, and then we try to reach an output or a formula, for the output signal where the modulation index beta and the modulation index beta starts to appear. Herein, we classify our FM modulation into 2 categories, actually, with respect to beta. For beta, very small with respect to 1, where we have what we can call a narrow band FM modulation, and with beta greater than 1, and what we can call a wide band FM modulation. And we say that this wide band FM modulation is somehow out of focus with respect to our course. So we go to the narrow band FM modulation, and we make use of the assumption that beta is very small compared to 1 to make some trigonometrical form to reach this equation, where we find that this is somehow very, very close, somehow very, very close to the AM double sideband AM modulation. Herein, we go to what's called the phasor representation. We start with the AM phasor representation, and then we go to the FM phasor representation, and we make then the final comparison between the AM phasor modulation and the FM phasor modulation. Now, let's turn to the other side. If you remember, in the final part, in the AM lecture, we deal with what's called the 2 main parameters that have a financial impact to the communication system. The bandwidth and the power. Herein, we can investigate it in the same way. So, knowing that our signal is typically close to the AM double sideband signal, herein we can use this concept in order to determine or in order to estimate the bandwidth for the FM narrowband signal. As you can see, you have a carrier, and you have another version of a carrier. This is actually a negative 90-degree shift version of a carrier, and you have the integrated message. So simply, whenever you are talking about the bandwidth, if you would like to draw the bandwidth of this signal, actually you will find that it is typically identical like the AM double sideband signal, where you have a carrier and you have lower sideband and upper sideband of the signal. So that's why for a narrowband FM modulation, what you are going to do is simply that you can use the normal bandwidth requirement for double sideband AM modulation, which is, if you remember, 2B, where B represents the bandwidth for a general M of T signal. So whenever you have a baseband signal with a bandwidth B, then the overall bandwidth will be 2. So this is the first requirement. Okay. Then let's turn to what's next. What about the wideband signal? Actually, as I mentioned earlier, we will not go into the mathematical details related. We will not go into the mathematical details related to the wideband FM signal, because, as I mentioned in part number 1, this is somehow complicated in the term of the mathematics. Maybe your colleagues in the other program, in electrical engineering program, go into details, but herein, due to it's a 1-semester course and we already more interested toward going into digital, we will not go into details here. However, we will just have a very quick look about the bandwidth requirement for the wideband FM modulation, and basically actually just making sense with using these terms. You can easily understand that for wideband FM modulation, you will need a wider bandwidth. That's why it's called a wideband FM modulation. So herein we have what's called a Kerson's law. You can check more details about Kerson's law actually in Simon Hyken in section 2.6. Here, this is a generic way, let me say, to model the bandwidth of an FM signal, saying that this bandwidth equals to 1 plus beta times B. Again, B is the bandwidth of the arbitrary M of T signal, whatever the signal is, and this beta is the modulation index. As you can see, as I just said, it's a generic rule. Why it's a generic rule? Because basically you can apply the same rule here on the FM narrowband signals, because in FM narrowband signals, beta tends to 0, or beta is very small with respect to 1. Let's me say like that. So 1 plus beta is simply 1, and then you can get what's a bandwidth of 2B, which is typically the same we have done together a few seconds ago. So you can easily use this law. Either you are a narrowband or an F-band or a wideband. However, with a greater beta, you can imagine that for a greater values or beta, then the bandwidth starts to increase. For example, typically, most of the wideband FM signals using beta equals to 4. So if you put beta here equals to 4, you can imagine it's 1 plus 4 is equal to 5. Then you have a total bandwidth of 10B. So that's why it's somehow critical that using a wideband FM signal will reflect to the overall bandwidth of the signal. So we need 10 times the bandwidth of the baseband signal in order to transmit the signal as a narrowband FM signal. So this is basically this is one of the major disadvantages actually of the FM signal. Maybe in the end of the lecture, I will make some sort of a quick discussion with you regarding the comparison between AM and FM signals or AM and FM modulations, and what is the pros and cons of every and each type of this modulation. Herein you can highlight one of the disadvantages for the wideband FM modulation, where you need a wide band, or you need a greater or larger bandwidth, can reach to 10 times the basic baseband signal bandwidth. So okay, so this is what's called the Kerson's law rule, one of the rules that can use to describe the bandwidth for an FM signal. So this is generally the requirements. As you can see, this is just a very quick comparison. Here is the carrier, here is the message. Now this is the AM signal, and this is a wide and this is the FM signal, and this is the bandwidth for an AM signal, and this is the bandwidth for an FM signal. And as you can see, the bandwidth for an FM signal is relatively larger. And this enlargement, I'm sorry, and this enlargement is function in beta. So whenever you get, sorry, whenever you get higher beta, you will get wider bandwidth. So this is somehow important in understanding the basics for an FM signals. So let's turn to the other side of the river. Let's turn to the angle modulation. And herein, in order to study the angle modulation, actually, we have to make some sort of, I would say, some sort of analogy with respect to the FM modulation. This is what we were going to do maybe later on. But here, let's remember, it's actually somehow a bit easier to deal with a PM modulation, because simply you just add the phase proportional to the message. So if I return back to my to my whiteboard starter and stop share screen. So starting from the generic equation for a carrier, you know that the carrier C of t is equals to AC cosine 2 pi FC t plus phi. So very simple. In order to integrate your message as a part of the phase, what you're going to say is that the phi is proportional to m of t. And to remove this proportionality, what you are going to say is that phi equals kp m of t, where kp is the phase modulation index. So generally, s of t equals to AC here, of course, s of t in case of PM. So s of t equals AC cosine 2 pi FCT plus KP M of t. As you can see, it's much easier than the case where we have a frequency modulation, because in the frequency modulation, you need to have some sort of integration to your message before integrating it into that modulated signal. Herein, we don't need this integration. It's just a direct proportionality to the phase. That's why it's a bit easy. So let's now return back to my PowerPoint presentation, please. And let's again open our laser pointer. So you can imagine here, from here, is that this is the three components for the phase modulation. This is the modulated signal in the case of the phase modulation, where the message is directly proportional to the phase. So herein some more equations, and herein some more relation. But actually, this is one of the important slides. Why? Now we just need to make some sort of analogy, let me say, between the AM and the FM. So let me now go again to my slides and see, or actually not see, let's write both equations. The equation for the modulated signal in case of FM, and the equation of the modulated signal in case of PM. So S of t in case of the FM is equals to AC cosine 2 pi FC t plus 2 pi K integration M of t, or M of tau actually, delta from 0 to t. Okay, so this is the general equation for SM, for the FM. What about the SM, the PM? AC cosine 2 pi FCT plus KP M of t. Okay, now let's do our analogy job. So as you can see, we have a constant amplitude impulse. The first term is identical to pi fct. And then we have two types of constants. And then we have either the message or an integrated version of the message. So this is basically the only difference. This is basically the only difference. So, for example, if I would like to use an FM modulator, we already, if you remember in part number 1, we already implement a simple FM modulator, if you remember. So, in the final exam, I told you, please, my dear students, you have an FM modulator. Using this FM modulator, please implement a phase modulator, a PM modulator. So, you need using this equation to implement a modulator to perform this equation. The issue here that in the FM modulator you have an integration. However, in the PM modulator you don't have an integrator. So, if you have already a differentiated version of the message, I mean, if you add here a differentiator, so whenever the message is M of t, then the message will enter the FM modulator in the form of partial M of t by partial t. Then, when this message enters the FM modulator, it will be integrated, as you can see here, and it's already differentiated. So basically, the integrator and the differentiator will compensate each other. So what you will get is this signal. Because now, just imagine that you remove this M of t and you put dm of t by dt. So simply what will happen is that we will have again M of t, because the integrator and the differentiator is two opposite mathematical operators. Using the same philosophy, however, this is somehow doesn't make sense with our progress, because we start with FM. That's why we start here with an FM modulator, because we already have the knowledge. We already have the know-how how to implement an FM modulator. But imagine that you have a PM modulator. And I told you, please use this PM modulator to make an FM signal. So it's very easy. Then you will have M of t, and then you will enter this M of t will be integrated, and then what you will get is simply this FM signal, because simply you remove this M of t and you replace this M of t by the integration of M of t. So it's an easy job. Sorry. So based on this analogy, my dear student, you can easily implement an FM modulator using a PM modulator, or vice versa. You can easily implement a PM modulator using an FM modulator. So let's now return back to the slides. So as you can see here, whenever you have a phase modulator, you just need to add an integrator here, and then you will get an FM signal. Whenever you have a frequency modulator, which is our first example, if you remember, we just add a differentiator here. That's why we get this M dot, which is a differentiation with respect to time, of course, if you remember. And then we have this frequency modulator. So generally, it's a very easy analogy That's why we consume a huge time, actually, relatively, of course, in studying the FM. And then just by using one plug, you can turn your FM modulator into a PM modulator. That's why. Another issue, actually, why we did not investigate PM in a very specific manner during this lecture. Actually, there is another reason for that, which is that we will going to do this phase modulation in more and more depth while we are considering the digital modulation, because actually phase modulation is very critical modulation technique while we are studying digital modulation. That's why we give a more focus on the FM in the analog, because in the digital we will be more and more interested to the PM. So generally speaking, and in order to conclude this lecture, we have generally 3 types of modulation while we are dealing with an analog message. The first one is AM modulation, where the carrier amplitude is changing with respect to the message. The second one is called the frequency modulation, where the frequency of the modulated signal vary with respect to the message. And finally, the third is the phase modulation, where the phase of the modulated signal is varying with the message. To have more and more, let me say, concluding way, in order to sum up what we have learned, we have to make some sort of, I can say, analogy between these 3 types of modulation. So whenever I ask you what is the main advantage of the AM modulation, I believe it's easy to recognize that. The main advantage of the AM modulation is the simplicity of implementation. If you remember, we came up with the idea that AM modulator is just an RF mixer. When you are going to multiply the message with the carrier, and then you can add the carrier if you are sending a double sideband. If you did not, if it's a double sideband surface carrier, then you will not add the carrier. So it's simply a one block of RF mixer that multiplies these 2 signals. So this is actually the main advantage. Another advantage comes up when we determine the bandwidth for an FM signal, which is relatively the small bandwidth. So in double sideband, it's up to 2B. Whenever it's go to a single sideband, it can be only 1B. So this is very, very, very important, actually, in our case. So this is another advantage. However, there is a main drawback with the AM modulation, which is what we can call the noise immunity. What I mean by the noise immunity, as you can see, the message is included in the envelope of the carrier. So whenever you have any imposed noise in the channel, for example, over this carrier, the carrier amplitude will be reshaped due to this noise. And accordingly, you will receive a wrong message because your message is indicated in the envelope of the AM modulator, or in the envelope, sorry, of the carrier. So the noise immunity for the AM modulators or for the AM technology is minimum, because whenever there is a change in the amplitude, you receive a wrong message. This is the main drawback. Okay, let's turn to the other side of the story. What about the FM modulation? For the FM modulation, we have very important advantages, which is actually the disadvantage in the AM modulation, which is the noise immunity, because here you have a constant amplitude. So whenever you have any imposed noise, you can easily detect and you can easily clip. You already have a constant profile for the amplitude. So this is a very good idea. However, whenever you are going to any arbitrary message M of T, you have to pay a lot in the term of bandwidth. If you remember, we do it together. When we put beta equals to 4, we found that we need a 10p bandwidth. So this is actually one of the main drawbacks while we are going to FM modulation. Finally, what about the PM modulation? We did not determine actually an equation for the PM modulation. You can check it using Simon Hayek in chapter 2 if you would like so. But without going into details, And just by observing this important point, if you remember, we already see this point in the case of the over AM modulation, where we have what's called the phase overlapping. And this is simply because your message is alternating from positive to the negative cycle. So your phase alternate, and automatically you see this phase overlapping point. And if you remember, my dear student, we said that for the phase overlapping, this will automatically reflect on the bandwidth of the signal, because this some sort of discontinuity in the signal. If you check your sinusoidal signal here and there, you will find it a pure, smooth, continuous function. However, here, discontinuity starts to appear, and accordingly, you can expect that the bandwidth will start to increase. So larger harmonics starts to appear. Herein, this is one of the main disadvantages for the phase modulation, where the phase of the signal, or sorry, the phase overlapping will lead to a higher component and then a higher bandwidth. Generally, this is an overview, and this is actually the termination for lecture number 4. But basically, my dear students, this is not only the termination for part number 4. This is actually the termination for the second portion of the course. If you remember in lecture number 1, when we started together the first lecture in this journey, I told you that we have a 3 portion in this course. The first portion dealing with signals and systems is somehow an extension for what you have already learned in your signals and systems course. The second portion were more toward analog modulation. It was a 3 weeks portion, starting with 2 lectures for AM and 1 lecture for angle modulation, including FM and PM. So now we terminated the second portion. Starting from the next portion, from the next lecture, we are going to do what's called digital modulation. And if you remember the basic block diagram, or the basic difference between analog modulation and digital modulation, is simply the message. In the analog modulation, you have an analog message, which may be my voice, for example. In the digital modulation, you have to digitalize this message. So your first step in the digital modulation, what we will going to learn in lecture number 8, or so in week 8, inshallah, is how to digitalize signal, how you can convert an analog signal into a digital signal. Maybe we have to ask a more principal question. What is the difference between analog signal and digital signal? And how we are going to digitalize our signals in order to have a digital signal. And then we're going to go deeply into different digital modulation schemes together. Thank you very much, my dear student, and see you next week with the third and the final portion of the course dealing with digital modulation. Thank you very much.